evaluate the definite integral from 1 to 2 of 2x squared times the square root of x cubed plus 1. So now the first thing we notice is this is a prime candidate for U substitution, because we have this x cubed plus 1 here, and if you take the derivative of x cubed plus 1, you get, well, not exactly 2x squared, but you get a multiple of x squared. So let's go ahead and see if that U substitution works. So let's call this U. So we'll say U is equal to x cubed plus 1. U is equal to x cubed plus 1. And then du will be equal to 3x squared dx. Now in our integrand, we have a 2x squared and a dx. So let's get rid of that 3, and we'll bring in a 2. We'll match it up with what we have. So we could divide both sides by 3. So du over 3 is equal to x squared dx. And then let's multiply both sides by 2. So now we have exactly the 2x squared dx. So remember, when you're making a U substitution, you have to basically absorb everything in the integrand. So you can't have any x's left over. So let's make this substitution. So we're going to plug this one in, and we're going to plug this one in. So now we have the integral from 1 to 2. The 2x squared dx becomes a 2/3 du. So let's put the 2/3 out front. 2/3 is a constant, so we can bring it out front. And we have a du. And then we have the square root of x cubed plus 1. Now this becomes the square root of u. So we could call that u to the 1/2 power. Okay, now this is something we could definitely and easily integrate using the power rule for integrals. Now, one thing to keep in mind, we still have x values here. So the limits of integration are x equals 1 to x equals 2. So we have our variable of integration is u, but our limits of integration are x's. All right, so let's perform the integration. So we have 2/3, and the antiderivative of x to the 1, or u to the 1/2, would be u to the 3/2 over 3/2. And we're evaluating this from x equals 1 to x equals 2. Now, in a couple of my previous videos, we applied this U substitution method of integration to indefinite integrals. And so the U substitution was just a temporary substitution. We went from x to u, then we did the integration, and then we converted the u back to an x. So I'll just follow that same procedure. And so, well, let's simplify this first. The dividing by 3 over 2 is the same as multiplying by 2 over 3. So that'll give us a 2/3 times 2/3 out front, or 4 over 9, times u to the power 3 over 2 evaluated from 1 to 2. All right, let's come over here so we have more space. All right, and so now that we've done the integration, well, u is the same as x cubed plus 1. That was our original substitution. U equals x cubed plus 1. So let's replace this u with the x cubed plus 1. So now we have 4 over 9 times x cubed plus 1. So replacing the u back with the x cubed plus 1. And that's to the power 3 over 2 evaluated from x equals 1 to x equals 2. So now our limits of integration are x values, and our variable is x. So now we could plug in the 2, and we could plug in the 1. All right, so we have 4 over 9. So if we plug in a 2 for the x, 2 to the 3rd power is 8, plus 1 is 9. So we'll have 9 to the 3/2 power. Then let's plug in the 1. So we'll subtract 1 cubed plus 1, which is 2 to the 3/2 power. And let's see, 9, Well, the square root of 9 is 3, and 3 to the third power is 27. So 9 to the 3/2 power is 27. So we have a 4 over 9 out front. 27 minus, and 2 to the power 3 over 2. Well, that's 8. That's the square root of 8, or 2 radical 2. I think we could go one step further and distribute the 4 9s to clean this up a little bit. So 4 over 9 times 27. Well, the 27 and the 9 will cancel, so that will be 12. Minus, 4 times 2 is 8, so we have 8 root 2 over 9. All right, so there's basically two ways of evaluating these definite integrals using U-substitution, and I want to talk about both of them in this video. So this first method is called back substitution. So with back substitution, what I mean by this is we're starting off with our variable being x, then we make a substitution to convert it to u, and then we make a back substitution to go back to x, because our limits of integration were x values. So as long as the limits of integration are x values, our variable has to be an x. So we went from u back to x. Now, so this is the method we used for indefinite integrals. So when we apply U-substitution to indefinite integrals where there's no limits of integration, we always back substitute at the end to go back to our original variable x, or whatever the original variable was. So let's talk about the other method, which this is the one I prefer, changing the limits of integration. Changing the limits of integration. Now, the whole reason that we had to back substitute was because our limits were x's and our variable was u, so they didn't match up. So we had to go back to x's, which we did down here in red. So now let's solve the problem again using, instead of back substituting, we'll change our limits of integration. So I want you to, it's probably a good idea to watch this so you can compare the two methods. All right, so we have the integral from 1 to 2 of 2x squared times the square root of x cubed plus 1 dx. And we're going to make the same U-substitution as before. So du is the 3x squared dx, or 2/3 du equals 2x squared dx. All right, so remember, these limits of integration. These are x values, and we're changing our variable, that we're using this u substitution, this change of variable substitution, to go from x to u, and that the whole purpose is to simplify the integrand. All right. So now we have the integral. So we have a 2/3 out front. This is exactly what we had before. 2/3 out front, u to the 1/2 power du. Okay, so that's exactly what we had up here. 2/3 times the integral of u to the 1/2 du. Now notice I didn't write the limits of integration, the x equals 1 to x equals 2. So changing the limits, we could change those x values into u values. That way we don't have to change our variable back to x. So what we could do here is use this. Use the fact that u is equal to x cubed plus 1. So when x is equal to 1, u is equal to 1 squared plus, or 1 cubed plus 1. So we're basically plugging in 1 for x and solving for u. So if we plug in a 1 here, then u is equal to 2. And when x is equal to 2, u is equal to 9. If we plug in a 2 for x, 2 to the third power is 8, plus 1 is 9. So these are our new limits. These are our new limits of integration. So now instead of integrating from 1 to 2, we're integrating from 2 to 9. And so now those limits of integration, those are u values. Which means once we find the antiderivative, which will be in terms of u, we could plug in the 2 and the 9. So that's 2/3 u to the 3 over 2 over 3 over 2, exactly what we had before, evaluated from 2 to 9, or 4 over 9 u to the 3/2 power, evaluated from 2 to 9. Okay, and now if we're using this method, we don't have to go back to, we don't have to replace the u with the x cubed plus 1. We just, with the changing the limits method, it's a permanent substitution. So that's 4 over 9 times, well, we'll plug in 9 to the 3/2 power, we'll plug in 2 to the 3/2 power, and that's exactly what we had before. That's exactly what we had right here. All right, so both methods always work, always. There's never a situation where you have to use one method rather than the other method. Like I said, I prefer to change the limits of integration. It's very rare that that's going to be more work. It's usually a little bit less work doing it this way. All right, and we still get the same 12 minus 8 root 2 over 9. So there you go. You have two methods for evaluating a definite integral using U-substitution. You can perform a temporary U-substitution and then back substitute using the original limits of integration, or you could use a permanent U-substitution, which I did second, and change the limits from x values to u values. All right. That does it for this problem. I hope it was helpful.